We talked about the wind-driven circulation and obviously, sorry, am I? Yeah. So why am I struggling with this? And we looked at this and we marked 1, 2, 3, 4. So we will look at what these mean. So at the poles, cold ocean water becomes saltier and denser from evaporation and ice formation. So when ice forms and water freezes, all the salts are rejected. That's called brine rejection. And if salt is left behind, that makes the water heavier and denser and make it sink. The cold salty dense water sinks and slowly spreads, and we will see that just like wind-driven circulation has certain constraints from Coriolis and from the fact that ocean has boundaries and you have to conserve mass and vorticity. Remember absolute vorticity and potential vorticity that we talked about. Similar constraints apply when dense waters try to spread into the ocean as well. And secondly, because there are no continents to block the water, the current can flow freely around Antarctica, as we mentioned several times. Some water moves into the Indian Ocean while another current travels into the Pacific Ocean. So we talked about this branch which is going into the Indian Ocean, which is blocked to the north, so gets converted into the surface water, comes back, but it also then mixes with the Pacific branch, where the deep and bottom waters are intermediate waters are going across the equator into the north over time, getting converted to surface waters, coming back through the Indonesian seas. This upper part of this is called Indonesian through flow, so that becomes part of this return flow, and some of the flow around here comes back, becomes Agulhas retroflexion, and this becomes the Agulhas current, and then crosses the equator again over here and transports heat across the equator from the southern hemisphere into the northern hemisphere. So there is heat coming across here and heat going north here. So this is the Atlantic meridional overturning circulation, there is an Indian meridional overturning circulation, and there is a Pacific branch of the thermohaline circulation as well. And paleoclimate shows us that in the past 3 to 5 million years ago there was also deep water forming here, but in the current configuration, current climate, we have deep water forming in the northern hemisphere only here in the North Atlantic, in the Labrador Sea and the Greenland, Iceland, Norwegian seas. Okay, so this crossing of the equator is confined again to be at the western boundaries. It cannot cross wherever it wants because of the changing Coriolis and the associated vorticity. So vorticity constraints apply there as well. And similarly here there is more complicated circulation near the surface because the changing monsoons, monsoonal forcing drive certain unique circulation here that we haven't looked at, but just take my word for it. And here also cross-equatorial transport of heat, salt, and so on happens at the western boundary current. By the same token, the water that sinks here cannot just go wherever it wants, and it's forced to follow the western boundary route as well, predominantly, again because of the same arguments we made before about potential vorticity conservations and so on. And of course the Southern Ocean is unique because it's a channel. Okay, so deep water surfaces in a process called upwelling are happens here. So the deeper waters are brought to the surface by upwelling and mixing. So it's simplistic to call it just upwelling. The warm surface current flows north towards Greenland, completing the cycle here. Okay, so how do we know that the deep water is getting converted to the surface water? Because heavy water is sinking at the bottom, the water is dense at the surface, the water is light, which is a very stable situation. Why do we assume that the water is actually getting converted on a 1,000-year cycle back to the surface water? Especially because if you go below a couple of kilometers, the currents are so slow that they cannot be measured directly at all. You have to use tracers, geochemical tracers in the water to infer circulation, and we will see one such example later on. Well, the answer is very simple. As long as you can go here and observe that water is sinking, convection is happening. When the water gets heavy, it sinks. That is convection, just like in the atmosphere when the air gets lighter by heating and adding moisture from evaporation, rises, expands, and forms clouds and rainfall and so on. In the water there is convection happening to the bottom. So as long as this water is sinking, you know that there is lighter water below, so the bottom of the ocean is not getting filled with heavy water and restricting the surface waters to the surface and deep water below. So as long as deep water is sinking, that means slowly that deep water that formed before is converting back to surface water over time. And it's also amazing that there are only 3 places in the North Atlantic and a couple of places in the Southern Ocean, Antarctica, where all the water that occupies such a vast ocean is being formed. That's pretty amazing. So all the near surface circulation is largely driven by winds and wind-driven currents. So the warm surface current flows north towards Greenland, completing the cycle. And here is an indication of how water cannot go anywhere it wants. So if you think about the polar region and the equatorial region, you have cooling happening and sea ice formation and salt being left behind, evaporation. So you have cold, salty water that sinks. So transition layer or thermocline layer exists, and you have deep spreading happening here along the western side of the boundary, and the cold water and warms and rises, and there is a lot of debate about where this energy comes from, because if you want to convert heavy water that can simply sit there but is being forced to become warmer and lighter, then you need a lot of energy. It turns out that a lot of the energy comes from the sloshing by the tides, and if the tides just move water back and forth, maybe there will be no sinking. But as the tides hit the mountains in the ocean, they produce waves and mixing, which slowly converts the heavier water below into warmer surface waters, and then there is also heating happening, which actually would stratify the waters and make it more stable. But this supply of water works with the heating, and then of course you have wind-driven circulation doing a lot of the work of bringing the warm water flow back towards the poles. So the main thing to remember is that the ocean is nicely stratified given the turbulent mixing and the mixed layer processes that we talked about near the surface, and the nice sharp thermocline in lower latitudes and deeper ocean. So water tends to follow isopycnals or constant density layers for energy reasons. It's easier to flow along isopycnals than across isopycnals in terms of the energy needed. So all I'm saying is that thermohaline circulation is also constrained to follow certain paths. So if you look specifically at Antarctica, then you have currents called the east wind drift, and then you have the westerly winds, which together with the ice formation create very, very heavy waters. So you have Antarctic bottom water forming, which sinks like a rock all the way to the bottom and spreads towards the north, mostly into the Pacific and Atlantic Oceans. And you have subtropical surface waters forming, and you have divergence and upwelling happening where the North Atlantic deep water that is coming south is being lifted towards the surface, and you have Antarctic intermediate water that is forming on top of it, and there is mixing of the two happening as well as the waters are getting advected again into various directions. So you have subantarctic surface waters, subtropical surface waters, circumpolar current circulating that water here in the Southern Ocean, as we saw before. Okay, so these pathways again are constrained by vorticity conservation requirements as before, so they cannot go wherever they want. Just to re-emphasize the differences in the processes of deep water formation in Antarctica, icy wind blows from the Antarctic continent here. So open waters, melting icebergs and freshwater fluxes happen. Salt is expelled as sea ice forms because it's also very cold. Cold, salty ice water sinks, forming Antarctic bottom water, which flows down slopes and so on, inundating, going north and west, as you can see here. So Antarctic bottom water flows westward in a boundary current northward toward the equator. So western boundary intensification kind of thing is not happening because it's a channel, but you have other constraints that happen. So every time you stretch the layer thicknesses and so on, and you move across latitudes, you're still subject to the potential vorticity constraint, remember, which is relative vorticity plus planetary vorticity divided by h, which is, let's say, a layer thickness. So less cold, less salty water sinks as well, forming Antarctic intermediate water. So cold, salty water sinks, salt is expelled as sea ice forms. So the idea is that in the North Atlantic, evaporation and salinity increase and heat loss in the ocean is the biggest control on North Atlantic deep water formation, whereas in Antarctica you have a lot of these other processes which are leading to Antarctic bottom water formation, which is some of the heaviest water, hence it's called bottom water, and you have lighter water forming Antarctic intermediate water, and you have North Atlantic deep water being pulled up by the Ekman divergence that's happening near the surface in the Southern Ocean. So this is all kind of descriptive, but we will come back and start looking at exactly how buoyancy flux actually looks at. So we have looked at temperature flux through heat budget, and we have looked at freshwater flux through salt budget. We have looked at momentum budget. Now we will try to put together the salt and heat fluxes together to produce buoyancy flux and see how ocean forms these deep and bottom waters and how that circulation gets set up and what it means in terms of vertical profiles of various properties, because when water sinks, it is taking heat with it. It's also taking carbon dioxide, oxygen and various other geochemical tracers. And when we come to looking at the ocean's role in climate change, global warming, then we will see how much heat is being taken down by the ocean in this process. Okay.